So for Jupyter Notebook, suppose you want to run a Python code. You come to new, you click new here, then you click on Python. If you want to run R, you click on R. So if I want to run Python, I click on Python. So this one would open a new script or a new page, and then keep in mind. So once you see this, it means now here we have a Python kernel here. So that's why you can see the Python here. If it is R, when you come here, you see R rather here, as you can see. So that is how. And then you can open series of cells with this plus sign to increase the cells. I've already covered how to use Jupyter Notebook and everything on my YouTube channel, so I wouldn't go much into how to use it. But as you can clearly see, it's much more useful. So it means now, let's go straight. So now we know how to install packages. Now, anytime you open a blog or something online and you've seen library of these, it means that these are packages that you need to install first before. Don't go straight and start using the person's functions and tell me or tell yourself that, why am I getting errors? It's just because you didn't load their packages. And then when you see the library, you can actually copy their library, try and run it. If you run and you get an error message that the package is not not available, then it means you need to install it. Okay, and to install, you now in Jupyter Notebook, you just use the install.packages and then in the same way I was telling you, and then you're good to go. Sometimes you can see these messages, but when you see this message, you can run it again and then it will vanish. So that is not a big deal. Now let's look at how to so working directory. We've learned how to set a working directory. And then, so it means that just go into the folder, copy, and then change so when you copy, automatically the bars here would actually slant towards the left. The goal is you want it to be towards the right. And once you are done, it means once you run and you are good to go. Here too, I've used this function to set up some specific size that I want for my graphs. I want my graph to have a width of 8 and then height of that, and I can set specific resolution. Suppose you want your graphs to be very nice, and so 300 is fine. You can increase the resolution, but the more you increase, it becomes too quality, and then too much of everything is bad. So I think 300 is perfect. So now, since I've set my working directory, it means I can now import several data sets. So now we are going to import several data sets. So it means in the folder, which I will actually share with the organizers, then you can practice, go through this. Now, keep in mind, all this script, I can download it as an RStudio file for you. All I need to do is that I go to file, and I go to download as, and I download it as R. I download it as R. I click on this, and I can also download it as HTML. So if I click on this HTML, now let me open the downloaded HTML file for you to appreciate what I meant. Now, so this is what I mean by the HTML file. So it means the same Jupyter Notebook I'm using. If I click on download as HTML file, this is what happens. It means if you send this to anyone, you just open with any of your browsers. And keep in mind, Jupyter Notebook works with any of your browsers. I usually prefer Google Chrome, so you can set Google Chrome as your default browser. Even when you are using referencing softwares like Mendeley, using Google Chrome sometimes it's quite straightforward for you. Anyway, so here you realize that you see everything I was doing. Now, if I should even come down, you see all the graph, I mean, the data, everything. But all these things you cannot see in RStudio after you've closed RStudio. Okay, so it means even if you save your R script in RStudio, you only see the script. You will not see this kind of information. But with the help of the Jupyter Notebook, you can see everything, including your plot, including everything will be there. Okay, and so that is the beauty about that. And once I send it to you, you can actually just copy and paste into your RStudio if you want to run. But I can also download it as an RStudio or a normal R script, and then you can also make use of it. Okay, so without wasting time, our time is fast spent. Let me just quickly go through. So now we've installed these packages, and then to load different data structures. So I'm loading the CSV. I told you for CSV we don't need a package. So it means I've imported a data called meta rate, and then these are the variables and so on and so forth. Yeah. So and then let's come down. So it means you can use the tail function, and then if I want to import a data which is already in Excel and I don't want to change it to CSV, then the package we use is the read Excel package. So why should I necessarily force myself to have to install a package in order to export or import an Excel data? Whilst I can just save the Excel into CSV, it won't lose any information, and then I can import it directly. Anyway, so here I just wanted us to stress ourselves. So it means you can actually import Excel data directly without the need to what? Without the need to. Now look at the difference. So here you realize that the head, after importing this data called transform data, you realize I can give it any name I want. That name that I've given to it is called the what? Is called an object. If you don't save this in an object, it means you cannot call it back anytime you need it. Now, since I've saved this as an object, I've saved the data with this object name. It means anytime I call Excel underscore data, it is the data that I'm trying to refer to. So here you realize that it also brought the first column was 1, 2, 3. It was just the index, and I don't need it. So I can now use the subset, right? So as I said, if I use positive of 1 here, it means I'm extracting the first column. If I want to exclude the first column, I can put negative there, and it will extract the first. It will ignore the first column and then print out the other columns. Suppose I want to ignore the first and the third column. It means I can use negative, bring the concatenate sign. It means anytime you want to extract more than 1, you always bring the concatenate sign, and then you specify which columns you want to ignore or eliminate. So when you do it that way, so for instance, let me just copy this and come to and click this and come to the next. Yeah. So here when I run this one, so you realize that I've excluded the first and the third. So I now have the element, which is the carbon. That is the only thing that I was interested in. Or I could just have put 2 here to just extract that information. Fine. So let's just go straight. Now I want to import SPSS data directly. So the SPSS data and then Stata data, there are 2 packages. So when you go up there, you see that there was a package called Haven and there was a package called Foreign. Both these softwares, these packages can help you import these these data formats. So now I'm importing SPSS, and we use read.what SPSS. If I was importing Excel, it was read underscore Excel. And then if I was importing CSV, it was read underscore CSV. Now this one would also export or import. If you are bringing something into the software, we call it import. If we are taking something out of the software into your repository, we call it export. So it means I can actually export this data. So for instance, this Excel data, suppose I want to save it as a CSV. Okay, I can use a function called write.csv in brackets file, the file name. I can just copy. So this is the object I want to save, right? This data I want to save it as a CSV, and then I can just bring this, the quotation, and just type maybe Excel underscore data, maybe CSV. I just want it in the CSV format, right? But or let me say new format or something. And then don't forget to bring the extension .csv. So now if I run this one, and now I go straight into let me go straight into my repository and see something. So if I go into my repository, can you see that we now have the Excel underscore data underscore new format? This means that you can actually import data and then also export any results you want directly into your repository. And this is the beauty of always setting your working your repository. Now let me just go quickly because there's no time. So now let's say let me calm down. Okay, so now let's say you want to import a Stata data. So for Stata we have read underscore DTA. Mostly the extension for Stata is underscore DTA. So it means you can also okay, this is another CSV data I've imported. So if I want to import this data, Stata data, so in order to run this with Jupyter Notebook, always Control Enter would run whatever is in each cell. This is what we call cell. Choose, because I'm doing a presentation. That's why I chose. You are seeing slide type. Ideally, the slide type will not appear because I wanted it to be in a presentation mode. So it means I could have gone to view, gone to cell toolbar. I chose slideshow so that you see slides. I could choose none, and then now you see it in this form. Okay, usually it's in this form. It's because I'm doing a presentation. That's why I've chosen slideshow so that you have it in a more presentation format. Okay, so this is how we import stata data. Okay, fine. And then if I want to import state, so this is stata with the Haven package. And we also have how to import data with the foreign package. With the Haven package is read_DTA. With the foreign package is read.dta. Stick to anyone you want. So this is just to say that you can import several data sets and work on several data sets at the same time in the same script you're actually building. Okay, and then you can actually combine the different data sets you can merge data set and everything. In my YouTube channel, I've already covered how to merge and so on and so forth. So this is also this is a SAS data, a data in SAS. SAS is also another programming language. When you go to US, most of them make use of SAS, just that R and Python are much more advanced than SAS. So it means if you know R, automatically SAS should not be an issue. And if you know everything SAS can do, R can do. But we cannot say for sure that everything R can do or Python can do, SAS can do. You can't say for sure. So here to have imported a SAS data. And then this is how, so it means you can import different data sets and so on and so forth. And so there are instances where, so if you look at, let's say the SAS data, so for instance, let's say gender, sex, it was entered or coded as 1 or 2. And I know that 1 means a male and 2 means a female. How to now change this 1 to 2? I've done all this before, but this is just a simple function to do that for you. So use the factor, and keep in mind you can use the $sign to extract a specific variable of interest. So it means that, let's say this is the name of this data, okay? And let's say this is the object name, and then I just use the $sign, I put sex here, and then it was, what was the name of that? Sorry, data. Okay, so then it means it has extracted the information on sex. I could have equally also used this and then also bring a quotation sign and type sex here, and it will also do the same job, but in this case it's extracted like a column and for you, fine. So there are so many ways to subset and extract information. So all you need to do is to use the $sign to call the sex variable, and don't forget is the sex variable equals factor of the same sex variable, and we are saying that 1 and 2 are the levels. Okay, keep in mind at this stage, when I imported the data, the software does not recognize sex as a variable as a categorical variable. It treats it as a numeric. So you realize that if I use something called class, okay, and then SAS_data, and then I use sex. Now, if I run this, you see it sees it as numeric. So the class is used to identify whether a variable is numeric or not. Yeah, so it sees it as numeric. But the moment I type as.factor around this one, it means I'm imposing it to be a factor. But keep in mind, it will not reflect here. I just want to see, even if I treat it as a factor, how many categories it has. So you realize that in this case, the moment I write as.factor, it treats it as now the class is now a factor. A factor means it sees it as a categorical variable. So don't forget that. So it means the moment I now say factor around this, and then in a way I'm also trying to impose it as now a factor, and I'm saying that anytime it sees 1, it means it's a male, it sees 2 is a female. So this is how straightforward you can assign names to some categories. Okay, and then suppose I wanted to see the levels. Now if I should type levels of, so you realize that in Jupyter Notebook, once you start typing, nothing pops up. But in RStudio, once you start typing, it pops up, and then it makes life easier. So you realize that once I type levels around of the variable sex, which is numeric, it says the levels is now. Levels is to extract the categories of a categorical variable. But the moment I say as.factor around this one, now you realize that it's going to print the levels as 1 and 2. So this means that if there are some variables, you know for sure that some variables are supposed to be categorical, make sure you set it as categorical before you perform your analysis, okay? And to set it as categorical, you can use this function, and then, so it means you can code it as a couple of 1 and 2s and so on and so forth. And then you can actually in R determine what 1 means, what 2 means, and so on and so forth. And then you can do cross-tabulations, okay? So you can use something called table of sex. It tells you to know the frequencies. So it means it tells me that the number of so here here we've added sex as this variable, right? Now, before I converted it into male and female, it will come as 1 and 2s. But now if I should run this one, it will come as male and female. Okay, and it tells me there are 132 males and so on and so forth. If I want to find corresponding proportion, I just have to divide by the sum of the sum of this table, and then it will find the total of all the observation, and then you can and to find the total, another way to do that is you can open you can just type dimension of your data. So your SAS, let's say the SAS data. So if I type the dimension, it prints out 2 things. The first one corresponds to the number of rows, and the next one corresponds to the number of columns. So it means there are 19 columns, and then there are 260 rows. And so it means I could actually, and the number of rows corresponds to the total, isn't it? And I can use the square bracket to subset the first information so that it will just print out the first how do you call it, the first row. The first is the number of rows. So it means instead of the sum, I could also just paste this one here, and then it will give me the same results. Okay, fine. All right, so now so now because in Stata they already assigned race. For instance, race is a variable. They set it as 1, 2 to 4. It has 4 categories or 5 categories. And in Stata, they already assigned that 1 means race of a student, and Asian. 1 means Asian, and 2 means Hispanic, and so on and so forth. But when you import it into R, it will still treat it as numeric, like 1, 2, 3, and so on. Okay, so it means we still have to set it as a factor. And to do that, all we need to do is now to still use the same factor we call race, and then how many levels is there. And since we already know the specific names of each group, we now assign the specific names. And now we can, if we should extract just the race, it comes out as this, and so on and so forth. So now quickly, when I come down, it means I can do cross-tabulation. So keep in mind that now if I want to find cross-tabulation between race and then sex, so it means once I type table, if I consider table of just one variable, it prints out just the frequencies of that variable, okay, across the categories. The moment I use another variable with another variable, it does cross-tabulation. And I can actually have three or 4 or more. So it means if I consider, let's say there's another variable called public, and the public was whether public school or not public school. And then so in Stata, it was assigned as 0 and 1s. So now it means that I need to, so if you look at public, now after assigning it 0 to mean this and 1 to mean that, now the public comes as non-public and public. Yeah, so that is an easy way to assign names to some categories. Now the moment I now bring, so here table, I'm bringing table of 3 variables. So what it does is that it will now split, it will do cross-tabulation of the first 2 across the categories of the 3rd one. Okay, so you can clearly see now we have public, and this is for the public schools, this is the cross-tabulation between between sex and then race, and then for non-public, this is it. So this is how simple you can do this kind of analysis in R. And then once you go through the YouTube channel, from beginning to the end, I think once you watch the first 4 videos, you'll be an expert to some extent in terms of the things you can do. You'll be fine. Yeah, so that is because once you're able to import data and you know how to install a package, and then you know how to create some functions of your choice, and there are sessions on how to create functions, then that is it. The rest is just the internet. The internet is your friend. Just make use of the internet, and everything you want to do has already been done. So it means if you want to do a generalized linear mixed model, just type how to do generalized linear mixed model in R, knowing clearly that you've imported your data and you know why you are using a mixed model. Okay, fine. So now let's and then it means that the CSV data that I actually imported, I can export it using the read.csv. And don't forget, you can also export it as an Excel file, right? It means here I'm exporting the SAS underscore data as a CSV file if they are interested in that. I can also export it as an Excel file, but keep in mind I'll need a package to do that. Always when you're importing and exporting an Excel document, you need a package. So why should you stress yourself? However, just for the sake of learning, we want to do that. So it means that we have a function called write underscore XLSX function, and that is what we use to what. So it's the same thing. The only difference is this. Now, this is the package. Now, keep in mind, if I don't want to load a package, okay. So if I don't want to load a package with a library, okay. If I don't want, so now look at something. If I take this off and I run this, it tells me that Excel underscore this one is not found. The reason is because I've not loaded the package that would cause it to run, right? So it means that if I know the name of the package, which I have already installed, so here I use the install.packages to install that, I can write the package name and bring these two columns. If I run, it will work. And this is another way of actually using a package without necessarily having to load it. But if I should take this off and then I should run this one, it means now if I run this, it will also work because I've now loaded it. So always keep in mind that, but it's just better you use the library, you load it, and then you don't need to waste your time trying to, restrict yourself to this. You get it. As in, trying to bring the two column and the package name is not necessary. Fine. So that is one thing you should note. Okay. And then here I created, so we are going to do some data analysis. The time is almost up, so I'm just going to go through, So I created a certain function to help student to do basic descriptive analysis. So it's my own function that I've created. So I like to call it Clement's novel function. So what I've done is that I've created a certain function that picks any data of your choice. But before you use my function, make sure that you have declared all variables that are categorical. So suppose gender, you coded it as 1 and 2. You've already used the factor function to declare that 1 means male, 2 means this, and so on and so forth. And then before you use my function, and always the class of your data must be a data.frame. So it means all the data that we've been working on. So if I type class of SAS underscore data, it means that it came as with 3 different extensions. So it means it's a data frame, is this and that. And with this, it cannot work with my function. We expect the data to be what? A data frame. So to make this to be a data frame, you can impose it by just using something called let's say data.frame. You realize that when I wanted to convert something as a factor, I said as.factor and it imposed it as a factor. So if I run this one, okay, and then type class of this, let me just type class of this. So you realize that in this case, the first one comes with 3 classes, but this one now restricted to a data frame. So keep in mind that your data must be as a data frame, and then you can now use my function. So what my function does is it picks any data, okay, and determine for each of your variables, okay, it determines whether the variable is categorical or numerical. If it is numerical, it computes the mean, the median, the mode, the standard deviation, skewness, kurtosis, some quantiles, even record it in 2 decimal place, and also plot histograms. Suppose the numerical variables are, let's say, 20. It will choose different colors for each of the histograms, okay? And then if the dependent variable is categorical, irrespective of the number of categories, it will find the percentages and plot and pie charts and put the percentages attached to the plot. So it's just a function I've created. It means I can actually convert it as a package, right? Now this talk is not going to talk about how to create packages. It means you can okay, so it means you can actually create your own packages and so on and so forth. Now, please, can you mute? Okay, fine. So here now, so it means in order to use my function, I wanted to summarize, let's say, SAS underscore data, and I had to bring as.data.frame, and then I want to give it a different name. Okay. Now my function, if you want to see my function, now let me just open my function from my script. And then I will share my how do you call it? I'll share that with you shortly. Okay. So now this is my novel function. So it means that I just created a normal script, right? So this is like a normal script I've created. And let me calm down. So this is a normal script I've created. So it means that instead of copying and pasting all this long function into my Jupyter Notebook, it will be too long. your code shouldn't be too long. So in that case, it means I can create it and save it as a separate R script and call this inside R such that R would only determine the specific functions of your choice. When you do it that way, it's just similar as loading a package. So it means now this particular function, now let me now, so this is the script that I'm talking about. It's quite a long script. It's quite a long function that I created. If you watch my YouTube videos, the first video, we started learning how to develop this function. Then each video, we're expanding it and we're expanding it further. And keep in mind, there are a lot of other things, but it was one of the objectives to develop this package. So I think by the end of the third video, we had already complicated the function. Okay, so now let me just quickly, we are almost wrapping up. Okay, so here, now, so the function name for my summary statistics is called summary_statistics. It's my own function, it's not a package. So it means you cannot load or install a package to get it. Now, if I should run this, it says that the function is not found. If we're using a certain function which requires the package and you also run a function without the package, it will also give you the same error message. Now it means that we can actually load the package, okay, sorry, the function that I've created using something called the source function. So you see, I created a very long script, and that script I called it novel_summary_computational script, right? Now I can actually copy the name of this. So if you remember, if you look at this, this is the name of the script. So it's the novel underscore whatever. So I copied the same thing, right? Or I typed the same thing. Let me share quickly. So I typed the same thing and just brought .r, right? And then inside the quotation, I bring the source. Now, if I should run this one, it's just like when you are loading a package. It's similar. It means you can actually create your own complex function somewhere. It shouldn't necessarily be a script only. You could have several functions in one script. But once you source it, it will identify each of the functions, and you don't need to actually, you don't need to type all those complex functions inside the same script you were using. So that is the beauty about calling external scripts inside your RStudio. Inside your either RStudio or whatever IDE you are using. So it means now the moment I use the source function, it's just like I've installed a certain package and I've loaded it. It's similar. So it means now I can remember initially we couldn't print this out. Now let's assume I want to view my function. I can now run this one, and it now prints out so this is how complex the function look like. I wouldn't go into the details. If you start watching the first video, you understand all this. So now let's make use of my function. So my function, this is what I've done. It means you can make use of it. My time is up almost. So it means all you need to do is that you specify the name of your data. And then if you set I to be, let's say 1, it will produce summary of the first. Now I just want the summary of the second variable. Suppose I don't even know the name of the variable. If I should run this, I'm coming. Okay, so this, and then yeah. So if I should run this one, it tells me the name of my second variable for the data is called sys, and then it was numeric, right? So it computed all these, and then it obtained some histogram plot for me. Suppose I specify the column to be 8. Now the variable, it tells me the variable is called ratio, and then it is also numeric. So it chose a different color for me. Now, if it's 13, it tells me the variable, this is the name of the variable. It also produces the median, whatever, and then we have that. Okay, so I think, just a minute, I think I was to declare, okay, okay, fine, let's just go on. Okay, so let me identify a categorical variable in this. So if I should print this out, so let's say sex. Okay, so sex is I think 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, so let's say I want to identify the 11th variable, the summary. All I need to do is specify, put 11 here, and then I run this one. It says a sex, it tells me the percentages, and then it produces a pie chart for me, and so on and so forth. Okay, so without wasting time, I've also created a certain function. Once you declare all the variables that are categorical, and those that are numeric is already numeric. Now this function will identify any variable that is quantitative. So it means that it's my own function that I created that you can use. So now let's say this is the data name is called meta rate. Now, if I now specify the argument as that data, it will print out all the numeric variables for me. And then if I should run this one to this extract categorical variables, and then if I print it, it implies there's only one categorical variable in that data. It's called southern. Now you can also do nice correlation matrix plots. And we use the package called performance analytics. And with this one, you can get this kind of graphs. You will never get this in SPSS or Stata. So it means you can see this kind of nice graph where you are doing a correlation matrix plot. The main row, the main diagonal is your how do you call it? It's your histogram, and then you have your correlation. You can choose if you want a Pearson, you want a Kendall Tau, you want a Spearman correlation, and so on and so forth. And then here, the lower diagonal or the lower triangle of your matrix, you have your scatter plot. Now, keep in mind, this helps you to identify if there's a potential linear or nonlinear relationship. So for instance, if you look at rate and convection, it tells me there's fairly a linear relationship between those two. Now, if you look at something like, let's say between FP and time. So always you look at the intersection and that tells you. So between time and FP is this one. So you can clearly see, it tells me there's some sort of quadratic relationship in there. So this helps you to know the type of other underlying relationship that might exist between that. It's unfortunate my time is actually up. And then this is where I was going to now talk about the interesting practice tasks that we wanted to use mathematics to identify or aid in a forensic research. You realize that in Jupyter Notebook, I'm able to actually paste a picture. As you can see, as you can see, I'm able to, if I should run this, I'm able to paste a picture. And so it's quite handy. Can I get just 5 minutes to take us through this experiment? And if not, maybe I'll end here, but if it's possible, can I get just 5 minutes to perform that?
Yes, please. You can proceed.
Okay, thank you very much. So now we have now learned about R or Jupyter Notebook, different IDEs, and I'm sure by now you are convinced that Jupyter Notebook is what you want to use. But for now, you can start with the RStudio, do stuff with it. When you go into my YouTube channel, the videos, I think the first 3 lessons I was using the RStudio. So it means watching the first 3, you'll be very familiar with the RStudio. But afterwards, I think the 6th video, I now showed you how to install, how do you call it, how to work with Jupyter Notebook and then go through the installation process and everything. So I think it's something you want to watch. Okay, so I was just there, right? During my PhD, I think I did quite a number of peer review publication in Cardiff. So I was interested in not just becoming an expert in my PhD, I was also interested in learning how do you call it, or becoming a more robust statistician, right? So I had my disease modeling, my disease modeling training in Cambridge, and every training program that I go for, I try to do a publication out of it. That is basically my style. So I work on a number of them, and then machine learning. I recently published a K1. It's a K1 publication, the International Journal of Forecasting, where I use machine learning for the first time in time series, but to do backward prediction in time. It's something that, I mean, you can actually learn. I think you just have to go to maybe Google Scholar and you search my name and you find all these, or just go to Google and you find all these, fine. But this one was a particular collaboration I did with someone in archaeology. So I was just there, and because I provide math support, I was a teaching assistant as well, and I was a math support instructor for Cardiff University. So I was just there, and one student from archaeology came and said, okay, she has this problem, and the problem is that you know, in the ancient times, the only weapon that was available was a knife and a spear, right? A knife, so a knife, and some people call it dagger, and then a spear. So those were the major, like, let me say, weapon type. You get it. And then they found some people who have been killed, and then they had multiple wounds. Some of the wounds look like is likely to be a knife wound, and some wound appeared to be like a spear wound. They were not too sure. And this happened ages ago. And then they wanted, the person wanted me as a statistician to help to identify, suppose an individual has been wounded with several wounds. Some wounds have different sizes, and potentially it meant some wounds were caused by a knife, some were caused by a spear and everything. How can I use a predictive model to be able to predict or determine or classify a particular wound, whether it was caused by a spear or a knife? And this brings us to a classical problem in regression called classification problem. So it means that this model or whatever I'm going to take you through, you can actually use the same thing when you are studying disease. Let's say you are exploring factors influencing the prevalence of a disease, where the disease is classified as whether you have the disease or not, or whether you are dead or alive. It's the same thing. So it means I can actually consider some predictors, and based on someone's information or predictive information, I'll be able to now determine whether the person is likely to suffer from a certain infection or to be diagnosed of an infection or not. It is similar to trying to determine whether a particular wound was caused by a knife or a spear. So that was the only thing that, if we are robust enough, you should be able to see that it was a classical problem in statistics. And to do that, we need the data, right? We cannot just go and get new set of people and just stab them with knives and spears and then get the data out of it and use the data, obtain a model, and then make prediction from it. We couldn't have done that. So what we did was to get something called pigs. So with the pigs, as you can clearly see, we gave them multiple wounds, right? So it means for a particular pig, there could be, I know this is a bit inhumane, but in order to be able to predict what caused that of, what actually caused the death of a certain mummy or Egyptian mummy or whoever, we needed to be able to do this experiment. So they actually did it. So they caused multiple wounds on the pig, which was already dead or slaughtered. And then some, they used the knife, some they used a dagger or a knife and everything. So it meant we got the data. So the data was saved so the goal was that they believe that, there's the whole hypothesis. They believe that depending on the muscle of the assailant is whoever is causing the death or whoever is causing the crime. Okay, the person, the assailant, and whoever, you are the victim, and in terms of the person who was being stabbed, they believe that the muscle mass of the person the assailant or whoever is causing the stabbing is more likely to influence the size of the wound. Okay, so that was one of the hypotheses. So we were interested in knowing whether, depending on how muscular someone is, could a person inflict more wound or higher or larger size of wound on individuals or not? So that is also one hypothesis, but we couldn't get a specific variable on the muscle mass of the individuals. And because of that, we use something called the BMI, that is the body mass index, as another measure to quantify the muscle mass of an individual. And you know that what the BMI tells how overweight or slim you might be. Okay, so fine. So here the data was saved in an SPSS format. So now we've learned how to import data into R. So now clearly we've imported this data. This data has been imported from SPSS, right? And these are the variables. So it meant that they had the BMI of the individual. And then the groups here represent the BMI category. So it meant the BMI we categorized into 3 groups as well. Fine. And then we know the area of the knife, we know the area of the spear, we know the length of the keep in mind the area of the spear, the area of the knife, and the length of the knife here. The area of the knife or the area of the spear is the area, but the length corresponds to the length of the wound. Okay, so the length underscore knife is like the length of the wound, and so on and so forth. So based on that, we now needed to do some hypothesis testing before we fit the model. So first of all, we wanted to check whether the archaeologist was only interested in comparing whether there was a significant difference between the produced incision area. So the incision area was just like the width and the area, the width and the area of the knife and spear. They wanted to check whether there's a significant difference between the BMI groups. So the BMI groups, these were the groups And then, so it means we are going to do a test, right? And keep in mind here, we are comparing two things, whether the two things are significantly different between a group of 3 levels. So one could have said, why don't you do separate ANOVAs? But I told you it's not advisable. But before then, you have to test whether the data is normally distributed. So since we wanted to test 2 variables or use 2 variables and compare whether it's significantly different between some groups, we needed to now do something called a multivariate Shapiro test. So in SPSS or in any other software, there are several ways of testing whether a data is normally distributed or not. So we have the Shapiro test, we have the Shapiro-Francia test, we have even the skewness and ketosis test. You have so many tests that you can actually do to tell you, even the Anderson-Darling test and so on and so forth. So here I did a multivariate test to check whether the 2 variables or the 2 numeric variables were multivariate normal. It came out that based on the p-value, keep in mind that the null hypothesis is that the data is normal, and the alternative hypothesis is that the data is not normal. So it means if you do a normality test, you expect the p-value to be greater than the significance level. Say it should be greater than, let's say, 5% in order to conclude that the data is normal. If the p-value is significant, it means your data is not normal. So don't get that twisted. So understand that for normality test, before a data will be normally distributed, we expect the p-value not to be significant. Okay, fine. To not to be significant means it should not be less than the significance level. Okay, so here, and we did a univariate test of normality. So this is the Shapiro test and so on. We also have Kolmogorov-Smirnov test there. And then the Kolmogorov-Smirnov test is like a non-parametric version of the Shapiro test. And you can also use to test your data, especially if your data is having very large sample size of more than 5,000. If your data has a sample size about 5,000 or below, the Shapiro test is much more effective than the Kolmogorov-Smirnov test. Fine. So here we did the univariate test of normality for each of the variable, and it also concluded both were univariate normal, and then combining them were bivariate normal. Okay, sorry, did I say both were univariate normal? They were not, the p-value is significant, so they were not normally distributed. And then in terms of multivariate normality too, they were not multivariate normal. And then, so it means that if you want to do hypothesis testing, you can only use non-parametric tests to test medians instead of to test means. And so this is a way of actually, and then there are graphical ways of also assessing normality. So we have something called the quanta plot. And then, so this is a nice way of doing that with the help of a package. So we have ggplot package, and then, so this is a function that helps you to get a very nice, so how do you determine whether a data is normally distributed graphically? Keep in mind, it's always better to do an actual test to make conclusion or inference. We don't make inference based on descriptive summaries. So it means if you plot the pie chart of males and females, and you find out that males were more than females with respect to something, you don't conclude that it means males are more likely to get that thing than females. The reason is because we don't conclude based on descriptive summaries. You have to do an actual inferential statistics, specifically test some hypothesis or fit some models in order to conclude whether your conclusion or hypothesis is true or not. So with the quanta plot, we expect these dots correspond to your data points. We expect them to be very close to the line of best fit. But here you can clearly see some deviation somehow, and that confirms why the actual test concluded the data was not normal. Okay, fine. So here, and then to do maneuver or to do maneuver or multivariate Kruskal-Wallis, you have to also test whether the variants are the same between the groups, or homogeneous or not homogeneous, and we use something called the boxes M test. It concluded that it's more homogeneous. Fine. So we went straight ahead to now. So this is just a way of comparing comparing the incision area. And that is with respect to the dagger across. Sorry, let me minimize this. Okay. Yeah, so to compare across the 3 BMI groups, fine. So these were just preliminary things with this. So here, this is a function to perform multivariate Kruskal-Wallis. I've already created it for you here. You can make use of it and perform. So it means most people go straight to maneuver, even when their data is not multivariate normal. Don't waste your time. You can actually do a much more effective one using the multivariate. I've created this function. I've given an assignment. The assignment is that cut and paste this function, save it into a separate R script, just like I did for the novel function that I created. And then also call it. So it means now, because if I run this one, it's because it's in the RStudio, then this will automatically what? This will automatically run. But imagine that this one was saved in a different R script, and you want to call it into R using the source function. So that is my assignment for you, so that you can just to learn that, oh, you can actually create complex functions in a separate script and call them into your current script, and then life becomes easier. All right, so now let's talk about the classification. I'm actually done. So this is the data. So you have to convert the data in this form. So it means that the ID corresponds to the IDs of the individuals who were actually causing the stabbings with the knives and the spears and so on and so forth. So if you look at this individual, at the point the person used a knife, at the point the person used a spear, and so on and so forth. And this was the length of the wound. So this length means the length of the wounds that was inflicted. Okay. And now, so that was the data. Okay. So I've imported the data. The data was saved in a CSV file. Fine. So here, when I imported the data, don't forget that we had A, B, C. And then we had BMI, and I wanted BMI to be categorized such that if you are between some range, we say you are in group A and B and so on and so forth. So here, this was a way of, this function helps you to categorize a numeric variable into categorical. Keep in mind, you cannot convert a categorical variable to numerical. Assigning 1 and 2s or dummy variables to categorical variables do not make them numerical. So keep that in mind. And though when you import, the system or the software sees that numeric, it's not numeric. So you have to invoke it as a factor. But if a variable is categorical and numerical, you can actually convert it to categorical. How? So you can say when it's less than 18, it means it's underweight. When it's between 18 to this, it is normal weight, and so on and so forth. Fine. So here, straightforward. Before you do this, you always divide your data set into testing and validation sets. Okay, so this function is just to divide the data set. You use about 80%, some can use 75% or 70% to fit your data. In that case, to fit your model. In that case, we say you are training your model. You always train your model based on a larger amount of data, and then you use a fee. You leave some, and then you now cross-validate it. By cross-validating means that we are going to predict the dependent variable for the ones that we left, and then we compare the discrepancy or how close, or check whether we're able to accurately predict the ones we left. Fine. So here we are using something called binomial logistic. The reason is because our dependent variable is whether the weapon type is a knife or a spear. And then that is our dependent variable. And our independent variable is the BMI status, which is quantifying muscle mass. And then we have, the length of the wound. And then, so we fit something called a logistic regression. And so this is how we fit a logistic regression. So if the dependent variable was continuous, we would have used Gaussian as the family, the error family. Since it's categorical, specifically with 2 categories, we are using a binomial. Suppose it had more than 2 categories, then you rather fit a multinomial logistic. Okay, so fine. So we are doing this fitting based on the training data set. So here it tells me that BMI, since you didn't see a star there, BMI was not significant, but the length of the wound was significant in predicting the dependent. This tells me that given the BMI and then the length of the wound, is saying that the length of the wound completely determines whether the weapon type, the wound was caused by a knife or a spear. So here, after fitting the model, we need to assess the accuracy of the model. So that's why we make use of the validation test data set, the one we left behind. So through that, we can now predict for the ones we left in terms of the response variable, the dependent variable. And then we use something called area under the curve. So this is like you compare something called sensitivity or specificity. All these things I'm doing, you can apply the same thing to disease modeling, where you are trying to predict disease outcome, whether an individual has a disease or not, or you can use it for survival analysis, whether an individual died or not. So everything I'm doing, you can actually replicate the same analysis for that. So this helps, and so keep in mind the area under the curve has been computed automatically, and we expect the area under the curve to be above, let's say 0.5, in order to say that the model was good. And here mine was perfect. So here you can clearly see the area under the curve is about 0.938, which is great. It's bounded between 0 and 1. So it can be negative. If it's negative, there's a problem. Okay, so here, so the area under the curve is one way of concluding the predictive power. And then based on the area under the curve, you can compute something called the Gini coefficient, which is much more a better accuracy measure. And it's also bounded between 0 and 1. And we expect, so keep in mind the Gini coefficient is basically telling the area, this is the area under the curve, but the Gini coefficient is also computed as a function of the area under the curve. It's basically the area under the curve minus 0.5 divided by 0.5 anyway. So and then this is the values. And if it's greater than 0.5, And then the maximum it can be is 1. But if it's greater than 0.5, it's good. And this is 0.7. So it means our model is great. If your model's predictive power is great, then it means that making inference from it is fantastic. And then we also have another statistics called the Kolmogorov-Smirnov statistics. Don't confuse this with the Kolmogorov-Smirnov normality test. And so this one is called Kolmogorov-Smirnov value or statistic that is also used to assess the accuracy, the predicted accuracy. So if you do any classification problem or logistic regression model or classification problem, there are 3 accuracy measures at least you can consider. You can consider the Gini coefficient, which is a function of the area under the curve. You can also consider the Kolmogorov-Smirnov statistic, which is also a function of the area under the curve. And you can also make use of something called the confusion matrix. By the confusion matrix, it means that you want to know how accurate we're able to make the classification based on the data that we left. So it means we predicted for the data we left. So here it tells me that my model was able to correctly conclude that it was able to conclude that a wound was indeed not caused by a knife, and it was also able to conclude that caused by a knife, and it was able to also correctly. So it means out of, let's say, I left about 24 data sets. It was accurately able to predict for 20 out of the 24 data sets. So it tells me that the percentage of what accurate. I think this one, the English. So here is percentage of accuracy. Okay. Anyway, okay. So yeah. So the percentage of accuracy, it means my model is 83.3% accurate. So it means I can now make predictions from it. So with this now, it means now we have the Egyptian mummy. Don't forget, there are 2 people, and each person has multiple wounds, a man and a woman. And then the multiple wounds, some wounds can be 5 wounds, some looks big, some look small, and we want to be able to correctly predict which of these wounds was caused by each of these. So I use this function to actually make, so when you do, this is a standard logistic regression predictive way of predicting. So it means once you fit your model, you can now use this simple. This is what we call so it's like you have the odds ratios, all right, but here we are actually using this simple linear expression, and then we can now compute the probability instead of the odds ratios. Fine. So here I've created a function that will do this for you. So it means you can actually extend this one. If you fit any logistic model with, let's say, 5 predictors, you can actually use this same function that I've done to actually extract the coefficient of each of the variables, and then you can actually make your predictions. Don't forget that we didn't know the BMI of the people who caused the wound on those who had died in some ancient time. We didn't know how big the people were. So we assume some range of possible values based on the data that we observed. So we assume that, okay, maybe let's assume that the BMI of a potential assailant was between 18 to 31, 31.5 in accordance with the observed data that we had. And then, and then the observed data, we were able to know the exact length of the wound for the man and the woman who had died in ancient times or who died ages ago. We're able to know the exact length of the wound. And I want to be able to predict each of these wounds, which one caused it. So now if I come back, if you come here, you can clearly see that now for this, the man had 3 wounds. The first wound had a length of 30 millimeters, and the other wound was 35, and the other wound was 60. And I wanted to be able to predict the probability that, let's say the green represents the wound length of 60. You want to know whether it's caused by a dagger or a knife. So here the probability, keep in mind that if the categories are 2, it keeps 1 as reference category. So it meant that here I'm computing the probability of the weapon being a spear relative to what? Dagger. So it means if the probability is high, then it means the chance of it being a spear is high. If the probability is low, then the chance of it rather being the dagger is rather high. Okay, fine. So if you look at this one, it means that if the wound length is greater than of 60, then the probability that it was caused by a spear was 1. So it was certain that a wound length of as high as 60 was caused by a spear. And when it was 30 is blue, you realize that it meant the probability that it was caused by a spear, depending on the BMI of the individual. So you realize that once how do you call it, is the wound length is smaller, the chance that it is going to be a knife is actually reduces over the BMI status. So this helps us to be able to correctly conclude whether indeed. So if you look at 35 clearly, you can clearly see that it means that the wound length was caused by a dagger, because the probability never came below 0.5. So it means 35 and 60 potentially was caused by a spear, whereas 30 was caused by a dagger. If you look at that of the woman, this is the kind of output. The woman was inflicted with about 6 different wounds, and each wound had different length. And from here, we're able to tell exactly the chance that it was caused by a dagger or a spear. And this brings us to the end of our meeting. And don't forget, once you get your results, you can also export some of your results. So here I was exporting some of the predictions. So I was exporting the probability of it being a spear relative to a wound based on the different wound lengths and so on and so forth. Fine. Anyway, so here I'm just trying to say that you can actually export some of your results directly into your working repository. So you now see the essence of the working repository. It's very useful. And so this brings us to the end of my presentation. I think I cheated a bit with your time. I'm sorry about that. But keep in mind, last year I had 3 days to take us through programming. But because of my current time and everything, here today we just did it once. And I think I've been able to achieve some specific goals. Now make good use of the YouTube channel. Please don't forget to subscribe. And keep in mind that if you want to get direct access to all the scripts on my YouTube channel, you just have to send me an email. Let me just write my email here. I think, so I have 2 emails. You can either send me through, email. So you can actually send it through either chumesi@cardiff.ac.uk, or you can send it through clements.chumesi@stats.ox. Okay, so here, if I run this, it will give me an error. Don't forget, because it's saying that the file is activated as a code. So I have to now come here and tell it that it is not a code. So if I choose head and see what happens, then it makes it big, right? If I choose Markdown, if I take this out, okay, and then I choose Markdown, then it comes at this. I can actually bold it. I can actually bold this one by using that. I mean, Jupyter Notebook is just fantastic. And I think I've convinced you why. Yeah, so once you send me an email, specifically through, you send it through my Cardiff email, because I've already forwarded most of the information through my Cardiff email. So send me the email through the Cardiff email. So once you send it, just tell me you want to be enrolled on the Piazza. The goal is just to be able to have direct access to all the files on that I use for the YouTube channel. And this thing that we've done today, I'll also upload it on the Piazza so that you can directly download from the Piazza. And then, yeah, so I'll end here. And if there's any other question, please let me know. And thank you very much. And I hope you enjoyed it.
Thank you so much. Thank you so much. We really appreciate your in-depth knowledge and for your time, the delivery. I really wish we would have more time, just as you mentioned, and we are so grateful to God you have a channel, you've given us links and then email addresses to be able to get in touch with you directly. So we'd like to zoom into our question time right now. Please, if you have any questions, all the questions you wrote down, this is the time to present them. So please, if you have a question, kindly look, find the raise hand button and raise your hand, and then you'd be selected to speak. So please find the raise hand button so that we can ask you to ask your questions. Okay, now we have Emmanuel. Emmanuel, can you unmute?
Fine.
And then
thank you very much, Dr. Chumasi, for a wonderful presentation. We are so grateful. Basically, I'm a nuclear engineer. I'm so interested in learning anything related to statistics to explore in my industry. I'll put it that way. Thank you very much.
Thank you.
And then again, a friend of mine also shared with me to analyze some data for him. And I realized that on today's lecture, There's a couple of questions I need to ask so that I'll comment out on it. First of all, he has about three, variables. It's more than three, but let me put it into three categories. He has a treatment, a control, and a time. So with respect to this, it's repeated variable. It's a repeated, like he did the experiment with time and time. So with this, he's so confused about the independent variable. Clearly, the dependent variable is known as the treatment group. So between the control group and the time, he's so confused. They want to consider for the independent variable.
Okay. So basically, in most instances, we don't consider time as an independent variable unless the person was really interested. And what you consider as your independent variable is always dependent on you, the researcher. So there are instances maybe you are just interested in ascertaining whether a certain predictor or a certain variable you believe could predict or could influence a certain outcome. So in that case, then it means that that variable that you believe could influence that outcome will be your predictor or your independent variable. Okay, so if the person is not interested in assessing whether time could affect the dependent variable, then it means that the data was collected over time and you can only consider it in your model as a random effect so that it will account for that temporal pseudo replication of data. And then the other variable that the person believes could influence the dependent variable should always be your predictor, and that is what we call the fixed effects. So the fixed effect variables are those variables of interest that you believe are your predictors, and it's always based on the researcher's choice. What I will consider as a predictor is because that is what I'm interested in exploring. You might be interested in something.
Okay, thank you very much. I think so clear now.
Okay. Thank you, Manuel, for the question. Please, do we have any other people with questions? Kindly indicate by raising your hand. Bali, do you have a question? Yes, please proceed.
My question, I have a problem with my computer. So my question is the function.
Unfortunately, I cannot hear anything.
Bali, we can't hear you. Can you type your question in the chat box so I help you read it out? Okay.
Only that's possible. And what's okay. Another person can ask.
Yes, please. Okay. No, the connection is bad. So kindly type a question. Please, do we have any other people, any persons interested in asking our doctor a question?
Sambiani. Yeah, please go ahead.
Can I go ahead, please?
Sure. Yes.
Thank you very much, sir, for the nice presentation. I very like it. It was very insightful also for me. And I would like to ask one question. It's about the last part, about the machine learning process. About the example that you show us, it was from a little or a small data set. You took a small data set, and from this data set, it seemed like you have just few data points information. I would like to know if that one is really representative for a quality of result to get at the end of our process.
Okay, thank you very much.
Thank you very much.
Yeah, so basically, before you perform any analysis, there's something called power analysis. So you can actually use power analysis to identify the minimum sample size that is imperative to achieve some degree of power in your analysis. And then in regression analysis, even a sample of over 30 or 50 is enough to achieve that. So when you say minimum, it means that anything above that would rather be an improvement, isn't it? But when you're in the context of machine learning algorithms, we usually require very huge data sets so that we can train the model effectively, meaning that more the data for the training of the model, the better. And but this we can still say is going to be representative, and the reason is why we actually left some and did a cross-validation. So it meant that if we had not cross-validated our model, that is the only instance we cannot say, okay, how accurate is our model, but we were able to now predict, even with these few data sets, we're able to still predict with accuracy of over 83.3%, and that tells that the model was good enough. But in view of, and also how large the data will be is dependent on your resources. So keep in mind that we couldn't kill, they couldn't kill so many pigs. And so it means they could just kill a few, and then sometimes I think they even made use of just a few of them, and then different people inflicted different wounds, and then they recorded it, right? So I'm not sure. So it depends on the cost and everything that will determine how huge the data will be. Now, this has brought to light my recent K1 publication with the machine learning under the in the International Journal of Forecasting. So what I did, which is something that I think should motivate several research in Ghana, was about blood demand prediction. And keep in mind, it has nothing to do with my PhD. My PhD basically develops stochastic and then stochastic models and other complicated parameter estimation techniques in the Bayesian framework to model biological systems, disease models, and so on and so forth. But because I'm interested in becoming robust, I do other things. So this is one of my collaborative research. What I did was that, in Ghana, we have improper database management systems such that we do believe the blood bank actually had a data of blood that has been demanded from the blood bank, but it only started from 2013 till date, meaning that all data before 2013 were completely lost. So when it happens that way, it means some very short data. And if you want to now make predictions, you want to learn trends, patterns from the data to inform policies, it becomes an issue. So, and then we know that we have machine learning algorithms or existing models that are able to, we can use to forecast or predict future in time. So what I did was to rely on the ability to predict forward in time, and then make use of that ability to also predict backwards in time by determining whether the data is time reversible. I wouldn't go much into the details. I think the paper is already published, and you can read that. And the beauty about that was that the series was short, was very small in size, but I employed a certain evaluation strategy called the rolling origin evaluation strategy. And by the rolling origin evaluation strategy, you can still train a machine learning algorithm with a small data set and still validate effectively and determine which one really has the best predictive power, such that for each origin, you end up getting a different error distribution. So it means you're going to end up getting a distribution of errors instead of just the fixed origin evaluation, where you just split your data set into testing and validation set, and you have a single error statistic. So it means when the data is very small, especially in the context of time series, the best way of assessing the predictive power of your model is actually to change the origin or the forecast horizon over time. And for each changes, you actually predict the predictive, you actually assess the error, and then it means you are going to end up getting a distribution of errors. I think you should get that paper, and then it will really inform you. And people can actually think about works where they are also predicting backwards in time, only if it's necessary. It was necessary to predict backwards in time because if we know the current data, and then all data before 2013 is completely lost, and then we can make use of or learn from what we know now, we can make use of that and also extrapolate. In this case, then backwards in time, we call it backcast, such that we are trying to at least get a fair guess of what the past values could have been, given what we know now. And that is exactly the contribution. And it was first of its kind. It has never been done before. And then, so it's a paper that I think you would want to check.
Okay, thank you very much.
Thank you very much. Yeah.
We'll take our last question because we're far behind time. We'll take our last.
Someone asked a question in the chat saying that when is structural equation? I mean, I said talk us through structural equation model. Okay, so basically with structural equation models, so there are instances in regression models, right? So if you look at the generalized linear models I was talking about, we were only interested in looking at the linear effect or the linear effect of the predictors on the dependent. We're not interested in exploring any other complex relationship even between the predictors. We're not interested in that. And we're also not interested in situations where the dependent variable could even be more than one. And when it happens that way, we could use multivariate regression. However, there are instances where for multivariate regression, it actually models each dependent variable separately. but it mostly doesn't explore or ascertain some potential complexity or relationship between even the dependent variable and also between the independent variable. So structural equation model is a way of trying to model a complex relationship, not just a linear relationship between a predictor and the independent variable. And in the process, we're able to identify not just which predictors were significant, because there are predictors that are not significant, but they could be significant in the presence of another variable. So it helps us to identify potential moderators, potential mediators. Mediating variables are like variables in their presence actually causes a certain variable to be significant. And then we have moderating variables, which are variables that actually causes the linear relationship between the two variables, or the dependent and the predictor, to either increase or decrease. Okay, so it means there are variables in their presence will cause other significant variables to be insignificant. So what I'm trying to imply is that with structural equation model, it employs two principles. It employs regression analysis, and the regression analysis, we call it path analysis. And the reason why we are calling it path analysis is because it's a set of series of regression models, or regression paths that has been developed. So it means it's just the normal regression you've seen, just that series of regression models. So we call it path analysis. And then it makes use of something called confirmatory factor analysis, not exploratory. So the confirmatory factor analysis means that it means when you want to do a structural equation model, you should have a fair idea the kind of complication or the kind of complex structure you think might exist in the data, even between the predictors, some that you think could be moderators and so on. But because you might not necessarily know which one are likely to be moderators and mediators, we do some preliminary analysis first before you do structural modeling. You can do something called hierarchical regression. It helps you. So with the hierarchical regression, you fit your model with, let's say, the first predictor. Then you assess whether the predictor was significant or not, and you determine the coefficient of determination, which tells the proportion of variance explained, right? And then you now add another variable in a stepwise manner. Now, when you add another variable, you check that the new variable increase the coefficient of determination. Was the change significant or not? And then they did reduce or increase the degree of significance. So that in a way, so it means if you include another variable at the second step, and it increases the coefficient of determination, it means that variable is likely to be what? It's likely to be a moderator. Suppose the first variable was not significant, but after adding a new variable, it first of all increased the how do you call it, the strength of the association based on the coefficient of determination, and at the same time caused the previous variable, which was not significant, to be significant. Then it means that the first variable, which was not significant, is only significant through, is indirectly significant on the dependent through that new variable that I added. So that gives you a fair idea about which variables could be potentially mediating or moderating. So it means when you perform structural equation, hierarchical regression, some people also call it multi-level analysis or multi-level regression. When you perform that, it helps you to identify potential moderators and mediators. You can even test whether some variables are indeed mediating or moderating using something called the Anderson-Hayes test. So there are certain tests that you can actually use to test all these things. So, but the hierarchical regression will give you a fair idea about potential, and then you further do the test. Then you can now construct a structure. Now the structure that you've constructed is what you are going to now use in your structural equation model. And then we call it confirmatory factor analysis because you already have a structure. You want to confirm whether that structure is that, or you have to reduce the dimension of the structure. That is why we call it confirmatory. Exploratory factor analysis means that you don't know the structure. You are now doing explorations to now get the structure. So I think that doing the hierarchical regression in a way is trying to explore some exploratory, it's not factor analysis, because we are not reducing dimension, but in a way we are trying to explore and identify potential patterns. And keep in mind that with factor analysis, the goal is to reduce the dimension, okay, of your data. So so it means it's possible that the structure you come up with, you will definitely reduce it further. And then how do you call it? What else should I say? So I think basically that is all you need to know about structural equation model. It helps you to model complex relationships that exist not just between the dependent and the predictors, but also between the predictors and also between set of dependent variables. And the most important thing is that your dependent variables or some of your variables must be latent variables, meaning that they must be variables that you cannot directly observe. Okay, so for instance, if in psychology, you might have variables, someone trying to quantify post-traumatic stress. And the post-traumatic stress or happiness score, or let's say sadness score, or whatever. And then they have series of items and series of categories. The set of categories that they are using to quantify, so for instance, let's say satisfaction. If I'm interested in assessing your level of satisfaction with respect to, let's say, some medical care, and I want to quantify your level of satisfaction, it could be that we have different categories, maybe satisfaction with the hospital, satisfaction with the kind of treatment you got from the doctor, satisfaction with different sectors. Those different sectors are called indicators. Those indicators, you can actually observe them because you can actually collect information about them. But based on those indicators, we now obtain a composite score of them, and that gives rise to the latent variable called satisfaction. And so it means that for a structure equation model, there should be set of latent variables in the model. So it means if you want to do structure equation model where none of your variables is a latent variable, then there's no need to use structure equation model. Some of the variables must be latent, meaning that they are not directly observed, but you can observe them only through some indicator variables or some constructs. And then you are interested in exploring complex relationships with the help of the path analysis. And then after identify the complex relations, you want to confirm. And that is where the confirmatory factor analysis also comes in. Yeah, so I think that is so far all I can say about that.
Okay. Thank you so much for your detailed answer. There's just one last question we are going to take from Mohammed. And then just as we are lucky to have the YouTube channel links, all materials from today's training would also be provided in the group. And also registered members would be sent materials also via their email. So we don't need to worry at all. So please, we would like to take one last question. Mohammed, kindly go ahead. And so we wrap up.
Okay. Thank you very much, Doctor, for the presentation. My question has to do with land cover prediction. So for instance, I have been able to classify data sets into maybe urban clusters, and then we have maybe forest and bare land and then cropland. And then I want to predict. Yeah, how do you do that in using machine learning? I mean, maybe I don't know whether.
So your goal is to predict for what?
To predict future land cover. Land cover.
So have you quantified land cover in any way?
Yes. So you have it. So you have maybe 2,000 land cover for 2000 and then 2020, and then I want to do for 2030.
Oh, okay, that's great. And then do you have some predictors that you want to also?
I want to pull some. Yes. So for instance, forest. Okay. I want to.
Okay. So now one thing you have to know about machine learning is very broad. So we can use machine learning algorithms for facial recognition, for even voice recognition. We can use machine learning to denoise images. So it means there are instances where you have a picture, like the picture's taken in some ancient time, and then you want to make it quite clear, right? So it means that we can actually, maybe due to bad camera or whatever or settings, we can actually use machine learning techniques to actually denoise or take away some of the noise or smoothing such pictures to get something nice. And we can use machine learning algorithms for time series forecasting, like I said. We can use machine learning algorithms for other complex systems, even in the context of computer science. And then we can use machine learning as a regression model. So what I did was a logistic regression, right? So it means that in your case, all you need to know is what is your dependent variable. It has been quantified. It is numerical. It is continuous. If it is continuous and you want to stick to, or whether it's continuous or not, I mean, whether it's categorical or discrete, whatever, you can use some set of machine learning algorithms in the context of regression. An example of that is we have something called the support vector machines. You can use something called classification tree, which is quite the basic machine learning algorithm. It's always good to compare between classes of machine learning algorithms and then conclude on which one has the best predictive power given your data, meaning that different data sets. So we can't say that, oh, this machine learning algorithm is the best. Different data sets will give rise to different candidates, right? So it means that classification tree is there. Some people also call it decision tree. Then we have random forest, which is somehow an improvement of classification tree. And we have something called the gradient boosting machines. And the gradient boosting machines actually is an improvement of the previous two. We have support vector machines is there. We have so many variables. And keep in mind, before you do your predictive modeling, you have to check whether you have to consider all your predictors or not. So you have to do variable selection techniques. You also have variable selection techniques in the context of machine learning. So there's one popular one called the Burrito algorithm. So it's one way of also, it makes use of classification tree and random forest to do that. And we have the recursive feature selection techniques. And we have different machine learning algorithms also for variable selection techniques. So always, whatever you want to do, the first thing is just Google. So know your dependent variable. So if your dependent variable is continuous, if it is disparate, it means in the machine learning algorithms, you have the ability to specify whether it's disparate or not, whether it's categorical and all sort of things. Okay, so that is one thing you have to note.
Okay, so I would like to do it maybe when I'm doing, and then I'll just send you an email so that you can help me out. If that
personally, I don't like helping out because sometimes I break down because I get so many, like everyone wants a piece of me, and sometimes it's quite difficult for me, and considering the fact that I'm currently doing my postdoc and other things and a lot of demands and those kind of things. So it's very, very stressful. And so usually what I do is that I can only advise you, but as to doing things for people, I don't do, but I can only send maybe relevant links, things that I believe should be.
That's what.
So for that, you can send me an email, and then I'm happy to, or you can call, whatever. I'm happy to just, especially, So that's it.
Okay. Thank you very much.
Thank you so much for your questions, and then would like to bring the question time to a close and proceed straight into our vote of thanks. All too soon, we've come to the end of the day one of our SkillUp training program. And then we were privileged to have our doctor in our midst, in the person of Dr. Clement Chumesi. We are far behind time, but we are so happy. People have learned a lot looking at the questions, and then even answering the questions. We don't even have follow-up questions. That shows how detailed the answers are. I must admit that I still have a lot to learn. So we would follow your channel. I would recommend to everybody here to go on YouTube, follow the channel. We have the email, just as he said, he's glad to send materials that would help us to figure out our works ourselves. So, I'd like to take this opportunity to start the vote of thanks. So first and foremost, I would like to thank all participants. All of you are the reason why we are having this training session. We are happy that you can pick one or two things from this. We would also want to proceed to thank the executive body of NUGS-China and GASCA, South Korea. We would also want to thank the specific team that pulled this together and made this possible. That is the SkillUp subcommittee of the academic committee of NUGS-China in collaboration with support from members of GASCA. Now, I'd like to quickly go through the names of these individuals. We have Delali, we have Isaac Safo, we have Abdul, we have Nat, Andrew, Muriel, Danny, and Esther, all the way from South Korea. To top it all, we have them being led by our Honorable Abba Shams, and that is why we are able to enjoy this education for free. So thank you to the hardworking team. And I would want to remind you, just as we kept saying throughout the program, the links, the materials would all be shared to you. Just keep calm. It's a 3-day program. Today was R. Tomorrow would be SPSS, same time, same details. So looking forward to having you all here tomorrow. Thank you for your time. And then before we leave, we'd like to show a special appreciation to our speaker today. So we have here a citation of honor. Tech team, can you please help me to project our citation to our honorable speaker for today? Yes. So from the bottom of our hearts, we want to express our immense gratitude to you for availing yourself. Just as you mentioned, you like to help people, and we have experienced it. We have gained some knowledge from you, and we are super grateful. So I would like to proceed to read. Citation of honor presented to Dr. Clement Chumesi. The National Union of Ghana Students, China, sincerely thank you for availing yourself to train the entire membership of the union during our SkillUp training on Introduction to R Programming, held on 1st July 2022. The event would not have been a success without your support. We deeply appreciate the in-depth knowledge you have shared and the willingness you exhibited in making our program successful. Thank you so much, Dr. Clement. And then we are very optimistic that this will not be the last. We hope that just as you were open and warm and receptive to our invitation, we will be able to call on you for such more training programs. Thank you so much, Dr.